So I'm Mike Stonebraker. My only job is to be the hook, which is when your time is exhausted, I will be the hook that yanks you off stage. So basically, we're going to have a chronology of Jim's professional life, more or less from beginning to end, in the course of the rest of the day. And I'd like to just set one piece of context, which is you guys we're all familiar and comfortable with giving technical talks, but I would much rather hear personal remembrances and war stories. So I will start with one myself just to set the tone. As you know, Jim is an avid sailor and has owned a sailboat, multiple sailboats for as long as I can remember. So he and Donna came to visit my wife and I at Lake Winnipesaukee, where we own a vacation house. And I said, oh my God, we have a speedboat. We do not have a sailboat. And Jim has routinely sort of castigated power on the water. And so I said, I was talking with my wife Beth, and I said, well, we should probably motor over to Wolfboro, which is like a half an hour ride, on our powerboat, for lunch, because it's a really lovely thing to do. But boy, is Jim going to be willing to, go out on a powerboat? And I can report to you that not only was Jim happy to go on a powerboat, but he loved driving our high-speed speedboat. So he is perfectly happy with stink boats. So with that, I don't have anything further, but I would just encourage everyone to talk about Jim while you're talking about whatever else you're talking about. And so we're going to start off with Jim in his System R days. And the Bruce Lindsay, who's somewhere around, is... So Bruce is going to come up and tell us about System R and hopefully tell us a bunch of war stories.
My task today is to describe Jim Gray's pivotal contributions to online processing technology while he was at the IBM San Jose Research Laboratory. Jim worked for IBM from 1972 until 1980. While he was at IBM from 1972 to 1980, he developed and implemented the foundational techniques that underlie and enable today's online transaction processing systems. Jim's contributions at IBM were made in the context of IBM's System R project. System R was a project, an experimental database management system constructed in IBM research to demonstrate that the relational model could be implemented in a full-function, high-performance system suitable for business-critical deployment. In 1998, Jim received the ACM Turing Award in recognition of his contributions to transaction processing technology and implementations. What is transactions about? Well, in fact, online transactions today are key to life as we know it. If the online transaction system stopped today, you would be stuck in Berkeley until they start up again. What about financial systems? Credit records, debit cards, identity theft. All these things made possible. Overbooking. Couldn't do that with without online transactions, could we? No fly list. Brought to you by Jim Gray. But in fact, online transaction processing technology is a critical enabler to commerce today throughout the developed world and increasingly in the developing world. Inventory, billing, sales, accounts receivable, customer care, payroll, fulfillment. All these are bookkeeping operations enabled by online transaction processing, which reduces record-keeping cost and delays. The cost and delays of record-keeping are actually part of the cost and expense of doing a transaction. And so if that expense can be reduced, both the customer and the provider benefit. In 1969, an ATM transaction cost the bank $5. Today, it costs the bank half a penny. These are the kinds of savings that online transaction technology is bringing to business and commerce. But bookkeeping has some serious requirements. The records must be available, reliable, and durable. And it's worth remembering that a single event in the bookkeeping world oftentimes, frequently requires multiple entries into the books. So it's not single event recording. Bookkeeping delays gate the flow of commerce, and finally, multiple bookkeepers over the same books must coordinate. Of course, multiple bookkeepers. If you got a second set of books, that's a different story. So, what did Jim do? He refined the transaction concept and told and explained to us what its basic properties were. Then he went on to show us how to do it.
You're an undergraduate, you're going to explain this to us?
You are the undergraduates, and you got to get this because this is important for you to know. Because it makes a difference to you, makes a difference to our world, and this is how it happened. First of all, Jim defined the notion of a transaction as a sequence of read and write actions, classified them into unprotected actions on the transient state outside the scope of the transaction, protected actions, the important ones. They permute or sense the persistent state of the system and must be reflected in the transaction outcome. And finally, real actions, actions on state external to the computing system, sensors and actuators. And of course, once done, these cannot be undone. All you can do about them is compensate them by further transactions. If you have fired the missile, actuating the actuator, well, you must compensate for that by debiting the quantity on hand and perhaps sending apologies. Given this classification of the actions an application program can make against the bookkeeping's persistent state, what other attributes should a transaction have? Mike Stonebraker mentioned acid. He was not talking about the 60s. Atomic transactions, the notion that the transaction either commits or aborts, and that the protected actions within the scope of the transaction are all or nothing. Can't have half of them. Can't move half the money from my account to your account. Consistency is defined as a sequence of actions, protected actions, taken by the application programming to transform the system state from one consistent state to another. So a correct transaction processing program assumes that it sees a consistent state and it produces a consistent state. Isolation deals with the problem of what about those two transactions executing that Mike mentioned. So if you understood Mike's example, when two transactions execute against the same set of books, there's got to be some coordination, or strange as things happened. And it's almost impossible for application programmers to sort that out at their level. And finally, durability, perhaps the most important point. Once committed, the protected state survives despite failures. Were these systems not able to preserve the committed state despite failures of hardware, software, everything up to and including perhaps fire, flood, and here at Berkeley, insurrection, must survive. Otherwise, these books are useless. We could not throw away the paper and the paper trail and go to online transactions if there's any significant chance that it's all going to go away at the unexpected moment. So all or nothing means that the sequence of protected actions defining the transaction are terminated by a commit or abort, but what if the system fails before either of those things happens? Well, in that case, we pretend that somebody said abort and must undo the effects of protected actions that have already been executed on behalf of the incomplete transaction. The other problem that we face in getting atomicity or all or nothingness is how do we boil down this sequence of actions against the persistent state into some single action against the stable state that represents the completion of the transaction? Well, Jim worked that out, taught us how to do it with a single write to stable storage that does not require that even the protected changes themselves be propagated onto stable storage. And finally, protected actions must be undone on transaction abort. If the guy says, do this, move the money from my account to Stonebraker's account, then the system comes to its senses and says, wait a minute, that's bad for Bruce. Abort. We've got to undo those actions. However, if we did say commit, and then the system failed before we managed to actually update the real accounts, it's up to the system to make that happen. And similarly, in the case of an incomplete transaction, to undo the partial actions that may have occurred already. Consistency. Now, consistency may be a hobgoblin of small minds, but it's often important in computing systems, and especially when the auditors show up. So the notion is that the protection actions within the scope of transaction transform the database system from one consistent state to another consistent state, although the intermediate states may not represent a consistent representation of whatever these books are trying to represent. Transactional programs should see a consistent state, which means it must not see uncommitted actions of other transactions, because that transaction may change its mind, or you may see half of the changes that that other transaction is making, and therefore see an impossible or inconsistent state. Of course, in order to remain sane, you must see the effects of your own actions, but otherwise you get up in the morning, you don't see yourself in the mirror, you begin to worry. To ensure transactional consistency, correct programs must transform the consistent state to a new state, must avoid changes to uncommitted changes by other transactions, and, interestingly enough, must prevent changes by other transactions to the state already seen or read by a transaction. This was not obvious to all of us in the beginning. Jim Gray taught us that. So how do you do that? Jim Gray invented the field of serializability by defining when are two application programs executing against the same data sets really isolated from each other? When do they not have to take into account that the other one might or might not be running? And he defined precisely what that meant in terms of obtaining a serializable schedule of those transactions, that the actual execution schedule can be reduced to a schedule in which one transaction runs to completion, followed by another, with the same outcome at the end of the day. That is, everybody saw the same thing in the reordered execution actions as they did in the original case. But enforcing absolute isolation or serializability is achieved only by introducing delays, restarts, and deadlocks into the execution of these application programs. These delays and restarts may interfere to an intolerable degree. So Jim Gray says, well, I can deal with that. We'll give them inconsistency if they want it. So Jim Gray not only defined how to obtain an absolutely consistent schedule, serializability, but he says, if you're foolish enough to move away from this perfect world because of reality, like deadlocks and rollbacks, well, here are some things you can do. So here's an example of a serializable transaction in which we've read here to item A. This guy on this side wants to update item A. He can't do it, even though, because the guy on the left has the right to reread that as many times as he wants and see the same answer. Not until the left-handed transaction is committed can we allow the update to A to proceed. One form of relaxed consistency, of which there are many, is called cursor stability. That is, you prevent updates only on the current item being read. Once that's moved on, you allow other transactions to do that update. Many transactions never come back and read the same thing twice, so they would never notice the difference in this case. And finally, the very dirtiest of dirty. If you really want to care, say, I don't care, man. This thing's just got to go. We don't care what the answer is. Go ahead, read dirty items. Let this guy on the left read A. Let this guy update it. Let him read it again and wonder why it changed. So this is important. Jim Gray invented this whole field. There were about 50 papers written on serializability theory. All of them had to reference his because it was first. And so this is pretty important stuff, and it explains to generations of database developers and implementers and users what's going on when you're running multiple application programs. So, given the idea of serializability, Jim described how to do it by simple locking, that you lock all the items that you deal with. If you're updating them, lock them exclusively. If you're just reading them, you can lock them shared. Hold all your locks until the end of transactions. In this case, of course, you can get a circular wait for condition. Deadlocks happen. Stuff happens. Well, you've got to detect that it happened and deal with it. Break the wait for cycle by aborting one or more transactions that are holding up the cycle. Well, that was great, but in many cases you find that, gee, we're setting an awful lot of locks, spending a lot of time setting these locks and releasing them, and golly gee, I wanted to scan the entire database. There's 40 million items. I mean, I got to set 40 million locks? Well, Jim said, let me think about that for 20 minutes, and said, here, I have an idea. Let's organize the system in some hierarchical manner, actually a lattice. For example, database composed of tables, and tables are composed of rows. And we make a new rule about locking, that if you lock a parent in the hierarchy, that implicitly locks all of the descendants, the children and grandchildren. So if you lock a table in share mode, implicitly locks all the rows in share mode. But adding one more rule to make this work, that in order to lock something explicitly in share or exclusive mode, you must first hold intention locks on all the ancestors of that in the hierarchy of that object. So better tell your ancestors what you're up to before you do it, is basically what's going on. But the intention locks, of course, as we can see by this little lock compatibility matrix here, are very nice. They like each other. In this little area here, you can hold intention locks compatibly for both intention exclusive and intention read. This allows bulk operations with fluid locking and is the key notion that led to the delivery of online data definition in the earliest relational database management systems, both in System R and in Ingress. And I would assert that the availability of online data definition operations in these systems was a key element in their acceptance in the industry and deployment for business critical use. It was now possible to change, add tables, add indexes without shutting down the whole system, which was the case for all of the database management systems of the day. So critical technology enabling critical feature. Well, what about the final letter of acid, durability? Well, that just means, like in Las Vegas, what stays committed or gets committed stays committed. Committed changes must survive processor storage, network, software failures, and this is the critical feature of online transaction processing systems that allows them to replace the paper trail with online transactions. In order to achieve this, because I said storage could fail, you got to do things very carefully, and you got to keep 2 copies. 2 copies of the books. Usually the bookkeepers don't like that. We had to explain to them, yes, there's 2 copies, but they really say the same thing. And in fact, the idea that Jim had and promoted is, well, you keep 2 copies. One of them's in this funny log format, which is just a record of what has happened. And then an optimized representation for actual use. So a database log for the real state, because it's the history of what's really happened, and an optimized database heap and indexes, and a protocol for making changes. And this protocol is quite simple and quite robust. Make the state change in memory, old state to new state in memory, and tell the log about that change. And not until that change on the log has reached it to stable storage, because when the power goes out, we're supposed to be able to recover. After the log has reached stable storage, then you can go ahead and promote the updated in-memory state on the stable storage. And on restart, you just do the right things. You undo uncommitted things, and you redo committed things. Well, Jim actually did his homework very nicely on the logging issue. And he said, well, maybe somebody thought of this before. Let me check it out. And he did find, actually 2 millennia ago, there's this guy, Theseus, an Athens citizen, who was sent to Minos, because Athens had to pay tribute to Minos. They had to send 12 children to be eaten by the Minotaur, who lived in the middle of this giant maze. Otherwise, Minos, King Minos, would come and beat up all the Athenians and break their houses. So they said, well, 12 kids a year, we got a lot of houses, we don't want them all broken. So they kept sending them. Finally, Theseus says, I'm going to take care of this. He goes over there, and long story short, he's stuffed into the maze, but he has a ball of string. Unwinds the ball of string, searching the maze, finds the Minotaur, slays him, but now he's got a problem. How are you going to get out of the maze? Well, he had an undue log. And the theme was, he said, well, gee, that's very interesting, says Jim. He said, I wonder if there are any other examples of early recovery technology that I should be aware of and cite. He says, well, gosh, there's this story of Hansel and Gretel. Remember Hansel and Gretel? Parents very poor, made the decision, we can't feed our kids, so we should abandon them in the woods. But Hansel overheard his parents talking, and he says, they're going to abandon us in the woods. That sucks. Got himself a pocket full of stones, and as his parents led him into the woods, he dropped stones along the way. No, stones. He had stones. No, read the story. He had stones. I'll finish the story. You'll get it. And his parents say, get the kids out of the woods. They say, wait here a second, kids, and the parents just disappear. But Hansel says, ha-ha, we got stones. Oh, stones, excuse me. Let's follow the stones. So they, again, an example of an undue log. Of course, it could have been a redo log. Parents could have followed the stones and found them, but parents wouldn't want to do that. So they got back home. Parents were a little disappointed. They said, gee, a plan did not work. Little known to Hansel and Gretel, they decided to try again, to redo. Their previous transaction had been aborted. But Hansel didn't have sufficient notice this time. They got out in the woods, so all he had was a loaf of bread with him, a lump of bread. So his tribe says, well, I'll just drop breadcrumbs, and we'll follow the breadcrumbs home. Parents abandoned him in the middle of the woods. They're all set. They follow the breadcrumbs. Here's breadcrumbs here. All of a sudden, no more breadcrumbs. A bird had come and eaten the breadcrumbs. This first known example of a log failure. So, like I say, Jim did his research, but in summary, Jim's tenure at IBM was spectacularly productive. He developed a model for transactional applications whose the properties of the model, allow online transactions to replace the paper trail and batch processing. He pioneered serializability theory for understanding transaction isolation and consistency, introduced relaxed degrees of consistency, invented multi-granularity, locking protocols, and refined the recovery techniques that enable transaction optimicity and durability. That's a pretty big contribution, because life as we know it depends on online transaction processing. Well, he implemented and published his results, which, as was mentioned this morning, have informed, guided, and inspired generations of database developers and practitioners. How many of you got early introduction to database through Jim's Notes on Database Operating Systems? Wasn't that a great paper? And finally, I cannot conclude without mentioning Jim's collaborative spirit and style. Working with Jim was a stimulating pleasure. He challenged his colleagues to participate in the development of his ideas, and he gratefully accepted their views and participation in refining those ideas. It was a lot of fun to go into Jim's office and just work on whatever he was working on at that moment. It was a great loss to IBM when Jim left the company in 1980, but we can note with pride his seminal accomplishments while at IBM, and we can congratulate him on his continued stream of important contributions in the years to come. I have 2 minutes left. I'll donate them to another speaker.
So I just want to tell two quick System R stories while we're getting ready for the next speaker. So as Bruce was saying, Ingress was going on in parallel with System R up the road 50 miles. And Ingress was a pickup team of 2 undergraduates, 2 grad students, and 1 staff person. And IBM put their normal quanta of resources on System R, which was about a dozen PhDs. So this was kind of David and Goliath kind of situation going on. But Jim was wonderfully magnanimous. He arranged sort of collaborative, what are you doing, what are we doing sessions between the System R guys and the Ingress guys every few months. And so I felt it was a wonderfully cooperative arrangement. The second thing is, many of you who have been in academia know that the best way to get code to work is to generate a deadline, and then student progress is exponential in the distance to the deadline. So to get Ingress to work, we would routinely invite Jim Gray and Ted Codd up for a demo of whatever we thought could conceivably possibly get done at the time of the demo. And we'd say, 2 months from now, we'll show you yada-de-ya. And Jim was always willing to come up and play the role of visiting celebrity to get this exponential progress. So again, I just thought he gave service wonderfully freely. My first PhD student was Jerry Held, and I think it was 1975 or 1976, 74. So Jerry went off to this little company called Tandem, which was 12 guys in a garage at the time, and started building what became Nonstop SQL. And so the next session is going to be on Jim's Tandem career, and John Nauman and Jerry Held and Wendy Bartlett are going to, I guess, come up and sit at the table. And so it's yours, and the hook will come in an hour or less.
We're from Tandem. We do distributed computing.
Are the mics on? Okay. One is on. Is yours on, Jerry?
Is mine on?
2 on?
Yep.
Wendy?
Anybody home?
Okay.
Yep. Okay.
We're some of the people who worked with Jim at Tandem, and we're going to talk to you a little bit about that. Jerry's going to start with how Jim got recruited to Tandem.
So to pick up on Mike's story, we had our little band of students at Berkeley, and I was kind of the chief programmer of that group and got to know Jim, and clearly the story that Mike tells is true, that we were driven when Jim and Ted Codd came up, because it was kind of a race between our little group and the group down at System R to get single variable queries working in joins and so on. And very shortly after that, I went down to help start the database group at Tandem, and we were a company that was focused only on online transaction processing. And it was a really exciting little company, and I put the emphasis on little. Jim was working at the biggest company, and I think many of you remember, but if any of you are young enough not to remember, IBM was so dominant. It's not like Microsoft today or Google today or Yahoo today. Wrap all of those together. IBM was dominant in every aspect of the computer business. And Jim was already kind of a legend, even at his early age at IBM. But at Tandem, we had a certain set of philosophies. It was a company that did lots of things. First, beer busts on Friday afternoon. We started sabbaticals and wonderful things like that. But we had a lot of philosophies on hiring. And so one of the philosophies was always hire people who are better than you are. And I was running the database group, and I was hiring a lot of really great people. But I thought, who was the best person I could possibly hire? And of course, that was Jim Gray. But people say, there's no way you're going to get Jim. He is like a legend already. He's at IBM, which is the best place to work, and he's clearly on track to be a fellow. It's pretty obvious he's going to be there for his entire career. But starting in '76, when I was at Tandem, and for the next several years, I'd see Jim at conferences, would meet with him, and tell him about a company that was doing just transaction processing and how we had a shared nothing architecture and how we had all these wonderful things that were a great vehicle for his work. And then I told him about a second thing, a philosophy we had, which was when you hire somebody, you ask them to accept the offer before you make it, which seems a little strange. But in those days, you didn't change jobs very often. It was a big deal. And if you made an offer, a financial offer, and somebody was considering two things, they could make the wrong choice because of the financial implications as opposed to what was really best for them. So we really did try to practice this, which was, if you have two choices, come back to me and tell me this is the choice that you want, and then we'll talk about the financial side of it. Not expecting people to really sign on the dotted line until I saw the numbers, but we want them to consider it. So on and on we went with these discussions over a period of several years, and in 1980, one day, my phone rings and it's Jim. And Jim says, I've decided to come to work at Tandem. I think it's the right place. The technical challenges are wonderful. It's a great thing. I said, so would you like to hear the financial offer? He said, no, you can tell me when I get there next week. And that is the truth. And he was just a guy who was, clearly he made a lot of money in his career. He did well financially, but it never was about the money. And he worked for 4 great companies, but it clearly was never about the company. It was Jim searching for moving the industry forward, the intellectual challenge, working with great people. And I thought that was just a prime example of what he was all about, and I really will miss him.
And Wendy's going to tell us a little bit about a contribution that Jim made sort of as an individual contributor just to Tandem, not to the industry at large.
Right, among other things. So Tandem was just a great playpen for Jim to land in. At the time that he showed up, we were building everything from our own hardware through middleware. We were pretty much all in one building, so if he wanted to follow his inevitable curiosity anywhere, all he had to do was walk down a hall or two. And so even though I was in the operating system area and he was in the database area, we'd intersect regularly even if we weren't working on something together. And so Jim was just, as you've all heard this morning and all know, was a great pollinator. He'd sort of go from person to person, and he'd take a bit of an idea from here and a bit of an idea from there and spread it around. And with that much stuff going on in that small of an environment, he was able to have a huge impact. But he also had a very practical side to him, and I think another theme you see in Jim's career is that, databases are nice, but what you're really after is you want to be able to take a bunch of data and do something useful with it. And so you see this on a huge scale with things like the Terra server. You see it in a much smaller but very practical scale for us at Tandem, because one of the first things he did was to write a little program called Telly. And in the days when org charts were, on paper and probably locked up in someone's offices, he wrote what's essentially the equivalent of the Outlook GAL. And so if you wanted to find out who worked for whom and where they were and so on and so forth, you'd just, type in a Telly command. And being Jim, there were a few Easter eggs hidden in there. If you knew the right incantation, you could get everyone's job code as well. So along with all the big thoughts and the work and the big projects, he'd pop up with these really handy little tools that you wondered how you ever lived without them. So the mix of, I think, the academic and the really pragmatic person was unusual and was one of the things that really made him stand out and helped him be who he was. So that was kind of the environment that he was in. As you've heard before, he was a prolific writer. There's a long, long string of Tandem technical reports. They're still out there on the web. And of course, he wrote about transactions and he wrote about messages. And one of the things that he did along the lines of, here's a bunch of raw seething data, let's see what we can learn from it, was to go take our outage data and start analyzing it, and wound up in, I think, 1985, writing a classic paper on why computers fail, where he went and did two different things. He took the reports that came in to our support organization about outages, and that kind of report's really comprehensive if you're looking at what the vendor screwed up, because if they think we screwed up, they're going to tell us. And it's kind of peters out. You hear about operational problems when they couldn't fix them themselves and they had to come ask for help. But if it was their own application, we'd probably never hear about it. If it was a power failure or something like that, then we wouldn't hear about it unless they needed help getting the system together again. So Jim did two things. He analyzed the data we had, and then he went out and made friends with the account teams for 4 of our big customers and got really detailed reports from them of everything that went wrong there, not just the kinds of things they'd tell the vendor about. So he was able to blend the two and make a really kind of balanced report on why computers fail, which, as he said, even at the time, is getting to be less and less about the hardware, and had some very accurate things to say about just how, a lot of the complexities driving in the software, it's driving in the management of these things. This is 1985, and that what you really need is self-healing systems so that you don't have operations people having opportunities to, intervene and accidentally make things worse, and so on and so forth. So he really ventured way past transaction processing when he was working with us to kind of, poke at anything else that was around that looked interesting. What I was thinking about what I was going to say today, about a week ago, I realized that he'd really been a role model for me in, this kind of boundaryless view of the world where, you turn into your manager's terror because you go poke at whatever looks interesting wherever it is, and you cross organizational boundaries and just, go for it. So I think that's something that I really got from Jim that I didn't realize how much I got from Jim until recently.
Okay, and what I'm going to do is talk a little bit about Jim's more specific technical contributions at Tandem. To start with, I met Jim when I was working at IBM on what they called at the time the Future Systems Project. Every company has a Future Systems Project, if you live long enough. And if you do, what you find out is that there's a lot of people who like the product you've got right now. This future system thing is not all that exciting. In IBM's case, since, as Jerry mentioned, IBM was enormous, the Future Systems Project was huge. It consisted of hardware, totally new hardware, and a totally new operating system, and to go along with that, a totally new database system. Jim started consulting with the Future Systems Project sort of on the side a little bit from when he'd come up occasionally to Palo Alto, where we were, and it was very interesting. He had some really good insights into things that we hadn't thought that much about. I was very young at the time, so I hadn't thought about a lot of this stuff. But even the people who knew about this hadn't given it as much thought as Jim had, so he helped us out a lot. The Future System Project, not surprisingly, collapsed under its own weight. IBM managed to salvage a lot of the processor technology into their follow-on systems, almost none of the operating system technology, and most of the database technology. The database technology that we worked on there was relational. We had actually 3 types, but relational was the one that survived in a product that IBM later shipped out called DB2, and you may have heard of that. Jim was integral in DB2. He actually transferred from the research group to the DB2 group when we moved to Santa Teresa, which is down south of San Jose. When I first met Jim, my immediate impression was one that you've all had if you've met him, and if you haven't, you've heard about it today, which was, this guy is really smart. He was motivated to do what he needed to do what he thought he needed to do, what he wanted to do, but he was also motivating. In addition to being able to get himself going, he could get groups of people doing things that nobody, certainly not they, thought were possible. That was amazing. In addition, he was very, very good at giving you ideas about sharing things with you. But as you've heard already this morning, he was also very good about listening to what you had to say. I think that's probably why he was so successful at motivating people, because people felt like if they didn't quite agree, they could go talk to him, and he would explain either why they were wrong or acknowledge they were right, and we'd move forward from there. That's a rare, rare trait in the industry, in my experience. At the time that I was working with Jim at IBM, he was commuting from San Francisco. He lived on a boat right next to Marina Green, and his commute was 75 miles one way. Now, this was back in the days of 45-cent gas prices, so it wasn't financially as bad, but you can imagine 75 miles on the road one way every day. He didn't make it home every night, but a couple of things came out of that. One thing was that he didn't much like the commute. It was only a little bit further than it was to the research facility at Santa Teresa, but at San Jose. But it was far enough that he started looking at other things. And Jerry's comments notwithstanding, I think that probably had something to do with why he decided to move. His commute got cut by 25 miles, and that was a big thing. He drove a Porsche, so it wasn't that bad driving, but still, it was 75 or even 50 miles. Obviously, working for Microsoft in San Francisco was even more desirable. A couple of things Jim told me, one of which was very strange, and one of which is very applicable to right now. The one that was very strange was, if pigs could fly, the sky would be black with pigs. I don't know how many of you ever heard him say that. This was something he used whenever anybody would say, well, gee, if we could just do this. Yeah, if we could, then, The other thing he said was, and this was when, after I'd known him for probably two or 3 years, he got me to start writing a paper, and he taught me to present the paper, or helped me present the paper. And I did this several times under Jim's almost insistence. He said, you never want to be between the audience and lunch. Well, the people sitting up here are between you and lunch. I'm going to take a little bit longer, but we're going to try to get you out of here as quickly as we can. Jim joined Tandem in 1980. In 1980, Ronald Reagan was elected President of the United States. IBM went to Seattle to talk to a small company called Microsoft about developing a basic product for its personal computer. Can you imagine a personal computer? Things were a lot different back then. The one thing that wasn't different was Jim. Jim didn't change a lot from the time I knew him at IBM until as long as I knew him. He was the same person. He was a caring person. He liked other people. He liked to listen. He liked to talk. He liked to eat. He liked to drink. He was a very interesting person. Some of the reasons that Jim moved to Tandem was probably commuting, but I think a lot of it was the other things that Jerry mentioned. Tandem was, as we look back, iconic for Silicon Valley. They had an open door, open management style. It was a very open company. They were very, very interested in recruiting smart and very highly motivated and strongly opinioned, I think the word earlier was opinionated, people. And Jim fit the bill. He was highly motivated. He was very strongly opinionated about the things he believed in. And so were a lot of the other people at Tandem. The thing that Jerry mentioned about hiring very good people, try to hire somebody at least as good as, if not better than you, was characterized in a mantra that Tandem had, which was A people hire A people and B people hire C people. And that's something I've carried with me throughout my career, and it's absolutely true. Find people who are really good, and you'll develop a team that's really good. And that's what Tandem was all about, recruiting the best people. I think that attracted Jim quite a bit. Jim recruited, he made an exception in this case, he recruited me to Tandem in 1981. At that time, the recruiting bonus at Tandem was $500. They actually paid you to recruit people. This was great. Jim didn't spend the $500. What he did with the $500 was take whoever he'd recruited and their spouse on a weekend junket. He took Franco Pizzulo, who he also recruited from IBM, and I, to the Ahwahnee Hotel in Yellowstone, in Yosemite, one winter, and it was a beautiful trip. I remember the drive up. We were in my Volkswagen, and we're driving to the Ahwahnee Hotel, and there was a bottle of champagne in the Volkswagen, and Jim decided to open it in the car. It took weeks before the champagne smell left my Volkswagen. Jim told me when I got to Tandem that you had to do an individual contribution. You couldn't just come and manage. I was hired as the manager of the database group. And he said, no, you can't do that. You've got to write something. So I wrote a program called Full List, which did exactly what Jim wanted it to do, which was take some data that was not easily available and make it available to people. It was a very good program. I mean, it was a good program, but it was very useful to people. That was what he really believed in, was making things that were useful to people. Tandem itself was the first computer company which was a commercial example of fault tolerance. It was designed to continue operation in the event of a failure of a hardware component, and maybe in the event of a failure of a software component, although that was a little bit dicier, as we found out. Clearly, hardware is not the only thing that fails in a computer, so we had to think about those things too. In 1980, Tandem was a $100 million company, which at the time was a large company. Not as large as IBM by any means, but it was a growing company. It was certainly a force to be reckoned with, a force on the horizon. They were the first company to do fault tolerance in a big way. They did it with a system called Nonstop. Everything, virtually everything at Tandem was called Nonstop. That kept us thinking about that. The Nonstop one was the hardware processor at the time. There was also a fault-tolerant operating system called Guardian, and a set of application development tools which were sort of rough around the edges, but not too bad. There was a Cobol compiler. Everybody in here's programmed Cobol, right? There was an application programming language called Tandem Application Programming Language. This was a C-type language, so it was relatively low level, but not assembler language. It was a good language to develop in. We also had a database management, or data management and database system called Nscribe, an Nform product, which did the query processing and which was relationally oriented, but really wasn't quite a relational product in the sense that we think of them today. Jerry might disagree with that, since I think he wrote a lot of it.
It was great.
It was great, yeah.
And furthermore, we're still using it.
Yeah, those things don't go away, particularly if they're pretty good, and this one was. The last thing we had was something called Screen Cobol. This was the way in which application developers who were used to writing Cobol programs could write a Cobol-like program that would actually interact with the screen. So the idea was that this would allow them to do transactions, whereas before all they were used to doing was batch jobs. After Jim joined, and Jim wasn't responsible for all of this by any stretch of the imagination, Tandem hardware and software evolved significantly. They went from the Nonstop 1 processor series to the Nonstop 2, and on through processor sequences, all of which were faster and better. I'll talk about what their characteristics were in a little bit. On the software side, we had something called TMF, Transaction Management Facility. There was a bit of TMF already there when Jim arrived. Jim and the group that he and I worked in took that from its vestiges to a very robust transaction management component, which basically implemented all the stuff that Bruce was talking about. This was astounding at the time. Nobody else was doing this kind of stuff. Write-ahead logs, where do you keep the log? Keep the data in memory because it's faster. All of this kind of stuff was new and exciting. He also worked on a product called Enable, which was an application program generation product, which allowed you to, with very few statements, actually generate the screen part and the database part of an application. And finally, Jim was integral in developing something called Nonstop SQL, Nonstop SQL, which was Tandem's SQL product. His technology contributions were enormous, but Jim didn't stop there. He went out to the sales force, as Wendy mentioned, and found out what they had, what information they had, and what needs they had. He also went directly to customers. This was not something that was normal at that time. Going out and talking to customers if you were a developer just wasn't something that you did. But this allowed him to bring insight to the technical products that we were developing at Tandem. I think through his career, certainly through the time that I knew him, Jim continued to look for customer and industry areas that needed to be evolved and developed. So he didn't focus on what was there. He looked forward. How do we make this better? How do we evolve it? How do we develop the next thing that's needed? Not the next thing that I think is a good idea because I'm a smart PhD in computer science, but what do people need and what can we do about that? The example this morning of the Terra server, I think, is a very good example of that. Jim wasn't thinking, I could do this. He was thinking, what do people need? What can they use? And what can we show them about how things work? While I knew him at Tandem, Jim evolved from a superb architect and developer, which he was when he started, to somebody who could and did make a profound effect on a business entity and, in fact, on the industry. I think his work at Tandem, while his work at IBM on System R was important and his work in Berkeley was important, I think at Tandem he started to suddenly see that he could make a difference in how companies worked, in how we interacted with customers, in how people got things done in a totally different way than we were used to doing. His specific contributions, I'm going to talk about 4 of them. Wendy said she looked through the papers. I did the same thing. There are order 50, 60 papers while he was at Tandem. There's hundreds more. If you're interested, there's a website. If you just Google Jim Gray, there's a website at Microsoft which has a list of all his technical papers. And if you go through them and just read the titles, it's a bit frightening to realize how much of a contribution he made. The 4 I've chosen to talk about here, the first one is transaction processing. Not the kind of transaction processing that Bruce talked about, but transaction processing in the sense of how people perceive it. When we worked at IBM, there was a sort of an ongoing effort to measure how well transactions ran. This was interesting because at the time, IBM had a product called IMS, which basically ruled as far as database was concerned. Most IBM customers who had database systems were IMS customers. There were a few who were using third-party, but not a lot. Basically, the model we used as we started looking at things in the DB2 project was a three-tier model. First, there was the sort application, then the batch application, and then the online transaction processing application. Each of those required measurement, and at the time, what was happening was people were mostly interested in measuring MIPS, or megaflops, or how many Wheatstones could you do. It was all about CPU speed. Jim looked beyond that and said, no, it's got to be about what the customer needs and what they're seeing. At the time that we started doing this, the fastest transaction processing system in the world, if you don't count the phone company, was a program called Airline Control Program, ACP, and that was run by the airlines. Now, the airlines had this problem of having to take transactions from their offices, from their ticket counters, from travel agents, and schedule flights and sell tickets. This programming system ran on IBM hardware and was capable of doing 800 transactions a second. 800 transactions a second in that day and age was unheard of. The way they did it was by ruthlessly curtailing what you could do in the system. And what that resulted in was a system that was not very easy to manage. IBM's IMS system had the same problems. In fact, most of the database systems that were in the area at the time, available from companies like DEC, had this problem of being very structured and very hard to manage and very hard to change. Jim felt that was a problem, and we'll talk more about that, but he also felt like we ought to be able to measure that consistently, because what happened when IBM did transaction processing measurements, guess what? They picked the best application for IMS, and they ran that, and they said, look how good IMS is. And when Unisys did it, they did the same thing, and when DEC did it, they did the same thing. So everybody got the application that made them look the best. Jim's contribution here was to say, that's not right. We need to find one application that everybody can measure against. The application that he chose was something that was originally called the teller cash drawer. Bruce talked about this a little bit. The idea behind this application was that a person came into the bank and either interacted with an ATM or with a teller. At that time, the banks wanted them to talk to tellers because they were cheaper than ATMs. What they wanted to do was either deposit money or get money out. Well, the teller had to send a message to the central computer and ask about this customer's account and see if there was enough money in it to satisfy the requirement, and if there was, get an assurance back that that was okay and that he could give them money. So it was a couple of messages going back and forth, a couple of database writes and reads, and then the cash changed hands. As Bruce said, we wanted to be very careful, everybody wanted to be very careful back in those days, about where the money was and when the transaction got committed. Early on, this was very difficult. But this was the application that Jim sort of took on as one that was easily understood, easily developed by the people who were going to be writing this for their systems, or customers who wanted to write it to see how their prospective systems would work, and it was easily measured. This teller cash drawer, evolved into TP1, which was this sort, batch, and interactive transaction benchmark. And that's provided the impetus for most of what's going on in the transaction processing measurement area for the last 20 or 30 years. So this is a profound application of not so much technology, but of thought. How do things work? In 1984, Jim wrote a paper with several other people at Tandem and elsewhere called 1,000 Transactions Per Second. This paper understood that you couldn't do 1,000 transactions per second at the time, but it talked about ACP, and it talked about how in the future maybe we could do that. The next year, he wrote a paper for Datamation, and the attribution for the paper was anonymous et al. He actually got contributions from, I believe, probably 30 people, and they're all listed in the trailer, but he decided to call it Anon et al., rather than attribute a title to it. This is the only case I can remember where what Pat Helen said this morning isn't true, where he wrote it all, but he didn't take the credit for it. There were a lot of very good ideas in this. It was the first well thought out, these two papers were the first well thought out discussion of how to measure transactions in systems and what they were good for, and how to basically reconcile what vendors said with what customers needed. The concept of the TP1 benchmark was the precursor to today's Transaction Processing Performance Council, and essentially most of the work that's gone on since then. Another contribution that Jim made was industrial strength SQL. While he was at IBM, Jim worked on the SQL product, mostly from the logging, locking, and recovery sides. He helped move those concepts forward in System R, and then he later moved them forward in DB2. But in spite of his efforts and the efforts of the other members of the team at IBM Research, SQL was largely viewed by IBM and by most of the industry, not Ingress, as a toy product. That is, it was not something you really wanted to use for anything serious. It was sort of this interesting, relational database, oh yeah, rows, oh yeah, joins, yeah, okay. Jim felt that wasn't right, and so in his inimitable way, he went and recruited a few people from IBM. Some of them are here today, Don Slutz and Franco Pizzulo, I have seen in the audience. And they came to Tandem, and we worked on nonstop SQL. Initially, this was supposed to do 4 things that Jim thought were very important for an SQL product. It was supposed to be integrated with the Tandem networking system and the transaction processing systems. This TMF thing that he'd been working on, we had to integrate this nonstop SQL into that. Really good idea. Nonstop access to data along the lines that Bruce mentioned. If it commits, it's there. If it doesn't commit, it's not there. It was also supposed to support modular growth. At the time, there's a centralized, decentralized discussion that I'll talk about a little bit, but at the time, most systems were centralized. The idea of modular growth was not something, it was something that people thought about and liked the sound of, but nobody could quite figure out how to do it. And finally, it was supposed to allow data execution across a distributed network. So the data itself was supposed to be in the network, and the applications were supposed to be in the network. There was continued skepticism in Tandem upper management. I don't think very much from Jerry, but he was on a different project by then. But from the CEO and the CFO and some other people about whether this really would ever make it. So Jim's role around nonstop SQL, once he recruited a team and helped with a little bit of the architecture, moved from being an architect/developer to somebody who was a cheerleader, keeping the team motivated, somebody who was a supporter, finding out new things that could help justify this, and finally somebody who was a protector. I was in meetings where Jim basically went head-to-head with people saying, no, you can't not do this. This is too important not to do. And he won those discussions. If you go out on the web today and Google SQL, you'll find 248 million hits. If you Google IBM, you'll find 270 million hits. That's kind of scary. Jim's ability to look at a problem that was coming, like the need for a faster and more capable and easier to use application development system, and to see how a data model that he'd worked on historically could satisfy that, was in no small part, I think, responsible for SQL's success today. It certainly wasn't the only thing, but it was certainly a big contributing factor. Another area where Jim was able to help by looking ahead, by knowing what he knew, looking ahead and finding out how things worked. Wendy talked about Jim's work on why computers fail. There's a couple of interesting things that came out of the paper he did on that. And one thing that was that Jim characterized as an oxymoron. The results were sort of interesting and unexpected. The major cause of failure at the time, and I would guess it's probably the major cause of failure in systems today, at the time it was 40% of the failures, was system administration. This is operations, configuration, and maintenance of the system. This is people doing things to try to get the system fixed or better or something like that. 40%. 30% was infant mortality at the time. This is software or hardware that arrived not quite right, either because it really wasn't quite right or the specifications weren't, the documentation wasn't quite right, something wasn't right. That's 30%. We're up to 70% of all the problems people have with systems. 25% was software. That's the software that we at Tandem were sending them or the software they as the customers were building into their applications. Only a quarter of the problems were like that. That's amazing. And only 5% were environmental problems, power failures, hardware burning up, things like that. The stuff that we protected for very well at Tandem from the hardware side was a relatively minor part of the problem that the customers were actually facing. Jim got two messages out of this. The first one was the key to high availability is to tolerate faults. If a fault happens, you have to live through it. You have to back the transaction up and make the data available. But if you do it right, you don't roll in a new processor, bring the backup tapes up and roll the data back and 3 days later bring it back online. It's all there ready to go. There's a backup processor that's right there that can take over and make things better. The second thing he found, which I just mentioned, is change causes problems. Change causes problems. But what he found as well was that most of the problems, the infant mortality kinds of things that customers ran across in this 30% were problems that we had seen at Tandem and fixed. So now we have the oxymoron. You should never change the system, but you have to change it as quickly as you can to get the new fixes in. Obviously, customers couldn't get this, and it was hard for us to get to. What are you going to do? If I change it, it breaks. If I don't change it, it's broken.
That one hasn't changed in 20-plus years either.
No. Things go around. The last area I want to cover is decentralization and scalability. Jim was, later in his Tandem career, after I had left, worked a lot on decentralization and scalability. Tandem systems were inherently scalable. It was a 2 to 16 processor system as the core, and those systems could be networked together to actually provide a much larger system. In the 1980s, the best example of a decentralized system was the telephone company. The telephone company had thousands of pretty large computers called switches and millions of terminals called telephones. They were all attached to a wire at that time. But if you think about it, that's a decentralized computer system. Today, the largest decentralized computer system is obviously the internet. So things have changed a little bit, but it's still a huge system with a lot of interactive things. In the 1970s, most applications assumed that there was a central database and central control. Tandem decentralized all that stuff, and Jim saw that as a real benefit. But he also said that there's no right answer to this. There's no right answer to centralized versus decentralized. Centralized provides you things like security and integrity in some ways, but it makes auditability, performance, and changeability much harder to do because everything's in one place. If I have to take the system down to change it, it goes down for everyone. Decentralized systems, well, there's no global knowledge. I don't know where everything is necessarily. I have to go find it. That's harder. On the other hand, the system is scalable, the system is robust and resilient, it lends itself to a client-server model. All those things are very positive. Jim's conclusion in his research into this was that there's never going to be a clear winner. It's going to depend on the application. But his work in the area foreshadowed much of what we see today in decentralized systems. And if I can get these last two pages apart, there we go. Throughout his career, and particularly at IBM, Jim recognized areas where ideas and practices would not be sufficient for what was going to happen in the future. And he became involved in those areas, and he moved forward in them, made progress in them, encouraged all of us to make progress in them. He did that with insight, he did it with research, he did it with papers, he did it with presentations, and he did it with products. There are a lot of people in academia who can look at their research. There are a lot of people in product organizations who can look at the products they've worked on. Jim was able to span that goal, or span that universe without any problems. One of the hardest things about talking in front of a large group of people is figuring out how to get away.
Well, I've got to...
Well, let me finish,
Okay.
and then you can say something. But so I tried to think of the one word that I would use to describe Jim. And I spent some time on this, and the word that I came up with was he was an explorer. In the purest sense of the word, he looked at the edges of the map and tried to figure out what was beyond them and how to get beyond them. And not only that, but the best part was he took us with him. And that's one of the things I loved about Jim. Thank you. Wendy, you had something to say?
Yeah. Right. Donna said that this session wouldn't be complete without a boating story. How many of you have gone sailing with Jim? How many of you have come back with tales to tell about going sailing with Jim? We've sailed with him off and on for the better part of 30 years and have a fair number of stories about them, but Jim got a nickname in our household after a 4th of July trip to the Delta with my husband Joel and Jim and his daughter Heather, who was a teenager at that point. And there was no end of things that happened on that trip, including discovering that you didn't have any gas when you needed the engine to make a landing at a dock, and waking up at 4 in the morning because the sailboat that you were towing behind the big sailboat is busy trying to stove in the sides of the boat. But my enduring memory from that trip, and I think the one that gave him his household nickname of Godzilla, was we're up there in the Delta, we're in the getting ready to anchor the boat, the wind's blowing hard, and so what Jim does is he takes the anchor, he drops it in the dinghy, rows to shore, and you see the back of Jim disappearing into the toolies with the anchor just, slung over his shoulder, getting ready to go wrap the chain around a clump of toolies and hope that they were going to hold us. So ever since then, he's been Godzilla to us.
Thank you.
Thank you.
Well, this is really great because we have 15 minutes before lunch, and so we selected people to tell about Jim, and we couldn't select everybody. So I'd like to invite, there are 2 microphones up here in the front, and if you knew Jim during the 70s or 80s and would like to share something, we have about 15 minutes that you could do so. Now, I know there are System R team members here. There's Don Chamberlain, there's Mike Blaskin, there's Guy Lohman, there's Ingress people here, there's Mike Ubel, there's, I think Bob Epstein is here, there's Tandem people here, Franco Patola and Don Slutz. So can I get you guys to, who weren't on the part of the formal presentations to come up and share a few words before lunch? Don't everybody come up at once. Okay, so just if you can share something, come up to the microphone and take a minute or two. So
I have 2. I'm Mike Blaskin. I work with Jim at IBM. I also went to Berkeley with him. My CS PhD is EECS, and his CS PhD is CS. Which one is earlier? I regularly went sailing with Jim when he had the H-28, the Herreshoff, the Japanese wooden Herreshoff. I had mentioned one time that man overboard was a routine practice that you should have skill at. We were out sailing underneath the Golden Gate Bridge with the wind above 35, and Jim said, "Man overboard," and jumped over the side of the boat. This is actually pretty scary because I'd done man overboard, but never in that boat, and never. That was a catch. It was not what I was used to handling. But we picked him up. We dragged him out of the boat. The other thing is, Jim he was a visionary. He was accomplished a lot. He wrote 10,000 lines of code of System R in a year, in addition to writing 9 papers. And in addition, we all know that he counseled everybody. He was everybody's best friend. I thought he was my best friend. Turns out he was 10,000 people's best friend, and I didn't know that, and I think most of you didn't know that. So how did he do that? Well, you know that he was very smart and that he was a nice guy. But what hasn't come out is that he worked so hard. This guy really worked hard. He would regularly, 2 or 3 times a month, work all night in his office. You knew this when you came into work to realize that he'd never left the office. I mean, he did work hard. So there's no magic solution here. Yes, be smart. Yes, be a good guy. Also work hard. Thank you.
Okay. And Margot?
So I'm Margot Seltzer, and I actually hadn't yet met Jim in the early 80s, but I was working for a company, and I was told to go build a lock manager. And every day I'd come in and say, "Oh, I've got it working." And my boss would say, "Well, Jim Gray says you can set a lock in 300 instructions. How many does it take?" and so we'd like, compile it down into assembly and count. And say, "Well, it's 450," and there was this amazing, incredible relief when we got it below 300. But my question for the rest of you in the room is that in 1983, we could set a lock in 300 instructions. And I challenge you today to find any system that can set a lock in under 3,000 instructions. And I want to know, where did we screw up?
Thank you.
Lynn Wheeler, I worked with Jim at research in the 70s. We used to have Friday nights after work, beer blast. And one night we were sitting around wondering how we could get the rest of the corporation to actually want to use online computers. And we came up with this idea that, well, maybe something like a telephone lookup command would be able to do it. So, but part of the requirement was that it would be a good thing if the whole rest of the corporation viewed using computers as a good thing. But in order to do this teleprogram, the requirement was he was to do his half in 8 hours, and I had to do my half in 8 hours, because that was the limit that we felt was on, the value of the rest of the corporation using computers.
So I'd read his papers, and I knew his name. And I was chairing a session I worked for Lawrence Berkeley Lab at one of our workshops on distributed computing. And this young man had just given a talk. It was basically based on some of the research he'd done somewhere, not at Cal. This person stomped down the aisle to the microphone in sandals with long, stringy hair. And he said, "That research has already been done. And he looked around and he said, "Who reviewed this paper?" Who reviewed this paper? He said to the young man, "I don't hold you responsible, but I want to know who reviewed this paper." And he was visibly angry, and he didn't. It wasn't no one answered, so he sat down, and I asked the person sitting next to me, "Who is that?" And they said, "Oh, that's Jim Gray." That's my next one.
Okay, thank you. Please introduce yourself when you give remarks, if you wouldn't mind.
Yeah, I'm Dave Riddell, and I first met Jim in 1969 when we were both graduate students here at Berkeley, and in particular working together on the Cal time-sharing system with a group of great people, several of whom are in the audience here today. It's certainly very appropriate that we're talking about both Jim's technical contributions and also telling boating stories, but especially given some of the pictures that have been shown today, I think we'd be remiss if we didn't tell any camping stories about Jim. Jim was one of the people who really introduced me to backpacking and the love of the wilderness. And I remember the first time, basically we got into the habit of every year, a group of us from the Cal Timesharing System project would go on a camping trip, which one of the participants lovingly labeled Nerd Pack. Jim came on most of those trips. He was so busy doing so many things, of course, that he didn't show up every year. But he was on a lot of the trips, and in particular, he was on the very first one. And I just remember that the other three people who were on the trip showed up with lots of freeze-dried food and fancy tents and packs and all this stuff. And Jim approximately threw a couple of apples into his sleeping bag and threw it over his shoulder and put on his tennis shoes and said, "I'm ready to go." And he basically spent most of that trip sort of gently laughing at the rest of us. And I remember coming away from that with this feeling that Jim had really taught me that the wilderness was my friend. I didn't have to be afraid of the bears. In fact, Jim complained about some of the places we went camping in later years that they didn't have enough bears and rattlesnakes to suit him. So I don't know, there was a whole attitude that I think rubbed off on me from Jim that I would sort of say was epitomized by something that I remember Jim posted on the wall one time in one of the wonderful old temporary buildings. I don't know how many people who were here in Berkeley in the old days remember the temporary buildings that were sort of, we thought they were going to last until the 23rd century. But he posted this thing on the wall, which was a translation of a haiku, and it's always really characterized something about Jim for me. It said, "Noble is he who thinks not when the lightning flashes, life is fleeting."
I'm Don Chamberlain. I worked with Jim on the Systemar project at IBM San Jose in the 70s, but that's not where I met Jim. I met Jim at the Watson Research Center of IBM in Westchester County, New York, before he came to California, between his graduation from Berkeley and his Systemar days. So I'd like to tell a story about how Jim came to move from New York to California. He and I knew each other pretty well in New York because we were both transplants from the Bay Area. And so we would get together and commiserate about snowing in the winter and things like that. Jim was in the mathematical sciences department at Watson Research Center, and he was doing some kind of mathematical modeling for urban planning. And I was working on an operating system project in the computer science department. And Jim really didn't like the winters in New York all that well. And at some point, he began reading some papers from a guy out west called Ted Codd, who was developing a new model for database systems. Jim thought that he'd like to go and work on that because it was warmer in California and because he thought Ted's ideas were pretty interesting. So he went to his manager and he said, "I'd like to transfer to California." And his manager said, "No, we don't want you to go to California. You're doing good work right where you are, so you should stay here." So Jim said, "Well, I quit." He got in his Volkswagen, he drove out to California, and he went and knocked on Ted's door and said, "I'm Jim Gray, and I'd like to have a job working with you." So Ted hired him, and so Jim came to California about a year before I did, and he knew that I was still back in New York, so one time he sent me a postcard. He didn't sign this postcard, but I knew who it was from. It was a picture of a sailboat with the Golden Gate Bridge in the background, and the only thing it said on the back was, "Need I say more?"
I'm Bob Horst. I worked with Jim at Tandem through the 80s during the time he was there. And I was in the hardware group, and I think it was a good example of how Jim was able to connect completely different disciplines together. And he gave me a lot of help in my early career in writing papers and so on. But one thing I especially remember is when he was working on the Why Do Computers Stop paper. That was a topic that was fairly sensitive inside a company who called its products nonstop. And so he did all this analysis and had a great paper, but it was a little touchy of whether he would actually be able to present that paper anywhere, given that we were selling nonstop computers. But he was able to convince the upper management somehow. I don't know how he actually did that. But that paper then came out and turned out to be a very important contribution in the field. So whenever I come up against someone in management and think of whether I can get something done, I think back on that. And if he could manage to get that paper out, I should be able to overcome any other obstacles.
I'm Ashok Chandra. I worked at IBM and currently at Microsoft. There are three little anecdotes I want to say about Jim. When I was at Watson, I'd heard about Jim. Of course, I hadn't met him there. But there was this project called System R happening on the West Coast. And we had, turned out in Watson, a competing project called Query by Example. And in IBM research, there was this discussion of what should really go forward as this database system. And Ralph Gomery asked three people, headed by Hirsch Cohen, Dick Case, and I was the junior member of this team, to go evaluate. Of course, we looked at the projects in Watson, then we went to San Jose. It was the first time I met Jim, Bruce Lindsay, Don Chamberlain, others. The team was really very special and spectacular, but we said, well, we ought to have a shootout. And we created a query to run, and the systems were set up, and the enter button was pressed simultaneously on both computers. And in the case of System R, and by the way, this was really run on the data manager, the lower level system which Jim had worked on. It came out like that immediately, whereas the other system kept going ka-chink, 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 ka-chink for a very long time. And we ended up coming back and recommending to Ralph that, oh, this SQL looks pretty good and System R looks pretty good as system, and we should have QBE, of course, as a front end. But anyway, that was my first time I met Jim, and I was incredibly impressed by him. My second anecdote I want to mention is later I was...
Okay, can you be brief, because
Right,
we want to get
sure.
through these three people
Right.
before
The
12:30.
second anecdote I want to mention has to do with an aspect of Jim that was perhaps not accentuated as much, was his competitive aspect. So we were in Almaden at the time, and Jim was in Microsoft, and he was running the Terra server, and we had something called the patent server. And we had this friendly rivalry. I would say, gee, I have the biggest system on the web, and Jim would say, no, he has the biggest system on the web, and I have 2 terabytes, which Jim said, I have 4 terabytes is what I would say. And said, but yours doesn't run on a database. Mine runs on a database, yours runs a file system. Anyway, so that was a real situation that happened. But finally, probably the most important one I want to mention is that Jim was the reason I ended up at Microsoft. He said at some point, yeah, sure, why don't you consider Microsoft? And I so, well, Jim's there, I should do so. So we built up a group and so forth. But 2 weeks before he disappeared, Jim came by to our lab and did a lab review. And one of the very special things I was able to do was in public to thank him for my being at Microsoft and for creating the team. And my takeaway from that is for people whom you love, whom you like, who've done things for you, tell them that you care about them, because you might not get another chance, and I'm glad I did that.
Please identify yourself and be brief.
I will. I'm Eric Ullman. I was actually one of those undergraduates on the Ingress project, so I knew Jim for a long time. But most recently, I worked with him on the ACMQ editorial review board. And one aspect of Jim's personality or talents, I guess, that hasn't been explicitly mentioned was his ability to simplify and make things obvious. Many, many times we would be having this big debate around the table, and people would be having a frank and comradely discussion, and Jim would be sitting very quietly at the end of the table, and then he'd start to say something, the room would go quiet. He'd summarize everything we had said in about 3 sentences, and we'd all go, well, that's pretty obvious, and move on to the next thing.
I'm Bruce Bailey, and I met Jim. He was teaching assistant for Mike Harrison on October 11th, 1968. And around 1981, I went to work for Tandem, and there he was in all his glory now, and a real famous guy. And he gave these Tuesday talks, and most of the people I'd worked with who were really smart were really intimidating. And we heard this morning about Jim as a mentor. He was a mentor because you could go to him and not be afraid that he was going to say, you are stupid. And other people would. And I think that people who worked with Jim, Pat Hillen spoke this morning, Pat Hillen became a mentor, I think, as well, out of example. I like to think that I've become a mentor to some of the junior members of my team where I work. And that's Jim as an example. So I would like to point out that Jim is, in fact, a mentor of mentors. Thank you.
Thank you. Okay, we are right on time. Lunch is out there. Be back at 1:30. Seating outside. Box lunches. Have a good lunch.